Okay, good afternoon guys. My topic today will be volume using the circular desk method. I am now on lesson number 63 on the topic integral calculus on my channel. And the last topic under integral calculus is volume. For the meantime, I am discussing using circular disk method. Okay. I will give you an example this afternoon, a popular figure in which we will derive the formula for taking the volume as a function of the radius. It's a sphere, it's the globe, it's the earth. Okay. We will derive the formula for taking the volume as a function of the radius. You know how the globe, how the earth is a graph. It's just like a ball, you know. So if they are asking for the total volume inside, what will be the volume as a function of the radius? There are some corresponding figures in real life which are actually a sphere, like the globe, like the basketball, the baseball, something like that. But if you've got a water tank in the configuration of a, what you call this, a sphere, if they will ask for the volume inside, you should know how to compute for the volume inside as a function of radius. Okay, let's proceed. The problem is derive by integration the volume of a sphere with radius r. We got a sphere and the radius is designated by r. So if we try to figure out our sphere on the Cartesian coordinate system, this is the y-axis, x-axis, draw a circle, okay? So if you are in front over here, what you will see will just be simply like a circle. But in reality, this sphere will be something like this, you know. If a sphere, it is something like this. Okay? So actually, it contains a volume inside. Like in the design of water tank, if the configuration of the water tank it will be a sphere, okay? It's a must for a design engineer to compute for, can compute, the design engineer can compute for the total volume that could be carried by a certain water tank in the configuration of a sphere. So actually, the problem is asking for the volume as a function of radius. We will be deriving the formula volume is equal to 4/3 pi r cubed. Okay. Okay, let's proceed. This is a circle for the meantime as seen from this. Okay. I will be using a horizontal slice. This is a horizontal slice. The thickness is dy. It is along the y-axis. And the variable radius will be xr minus xl. As this differential area moves from the horizontal line up to this point here, okay, actually this differential area is a variable. Okay, it's a differential area, it's a variable thing. At this point here, it is largest. As it goes up, becomes smaller, you know. So actually, you could not just use the formula for taking the area of that like in a rectangle. A rectangle will be a straight line. This one, it is a circle, you know. So the radius of the variable area is actually r. This point here is xr. This point here is xl. Okay. And if we try to rotate the horizontal slice, one complete revolution with respect to the y-axis, the configuration will be something like this. We rotate this differential area, one complete revolution. Okay, this will be the configuration. Okay, the area of the circle will be this one shaded by the blue line. Okay, we rotate it one complete revolution, okay? And the thickness is dy. So to compute for the volume of this thing here is variable. As it moves from 0 to r, this volume here is variable. That's why we need integration, okay? So differential volume will be the area of this times the thickness, okay? It is this. Differential volume is differential area times thickness. It is the area of the circle times the thickness. That will be differential volume. Why differential volume? Because this is differential area. This should be differential volume. Okay? Differential volume now will be equal to, we are now bringing out the formulation of the equation and how to take the integration. This should be pi. Differential area is pi times the radius square. The radius is 6. I just place radius quantity square times dy. Radius from the given figure, first figure number 1, radius is actually xr minus xl. Okay. This is the variable radius. So it should be xr minus xl as this differential area moves from 0 to r. Okay. xr minus xl. xr is actually the square root of r square minus y square. This is circle. xl is equal to 0. It is a straight line. So actually, we are taking the area between this line here and this portion of the circle here. This is a circle and this is a straight line. And we know the equation of this circle here. If the center is at 0, 0, the equation of the circle will be x square plus y square equal to r square. Okay, I will erase this one. I put it here, xr is actually the square root of r square minus y square. Because in here, x square plus y square is equal to r square. Okay? This x here is actually the xr. Solving for x square equal to r square minus y square. Okay? Then take the square root of both sides. These two here cancel with this. X now, I will now place the subscript r. It is this. It is the variable x of the circle, okay? Equal to r square minus y square raised to the 1/2 will be the square root of r square minus y square. It is this. Okay? And the equation of this, no problem, it's a horizontal line. xl is equal to 0, it is a straight line. Therefore, we go back to the radius now. Radius now will be equal to xr, will be the square root of r square minus y square minus 0. Okay? Or simply, radius will be r square minus y square, the square root. So if we try to take the square of both sides, okay, radius square will be radius square equal to r square minus y square square root. This is square. So it is actually something like this, r square minus y square raised to the 1/2. Then we raise that again to the second power, so these two here cancel with this. So what will remain on the right hand side after this squaring is radius square will just be simply equal to r square minus y square. Going back to the differential volume over to now, I place 2 here because this pair is actually symmetrical with respect to the y-axis. To take the total volume, just take the volume, the upper half, then times 2. Okay, so this is over 2. Equal to pi times r square, which is r square minus y square plus quantity dy. Okay, let's bring out the lower limit. Lower limit will be 0, higher limit will be r. Our limit will be an ordinate. And this dy here should move from this ordinate here up to this to cover up the total area, okay? Then we rotate it. So actually our lower limit is 0 and our upper limit is r. Y lower is equal to 0, y higher is equal to r. So this is with the limit from 0 to r. Going back to the integration now, if we try to integrate both sides, sorry, I should buy a new ink, guys. We take the square root of this. The square root of the differential b over 2 equal to, we bring out pi. This is pi, the integral from 0 to r square minus y square dy. Okay, then I will multiply both sides by 2 here. This 2 here cancel with this. Left hand side will just be simply the integral of dv equal to pi times this quantity times 2 will be 2 pi. Is the integral from 0 to r of r square minus y square times dy. Okay, volume now will be 2 pi. R square is constant, so the integral of r square dy equal to, we bring out r square, the integral of dy. So it will be r square times y. So the first one, the integral will be r square times y. Second one, it's an easy money, guys, power formula. So this should be y to the third power, 2 plus 1, which is 3 over 3, with the limit from 0 to r. Volume now will be equal to 2 pi. R square, we will place the upper limit to be r, y to be r. So this is r square times r minus r cube over 3, close quantity, minus 2 pi, minus the value of the lower limit. I just copy this one, I will subtract the value of the lower limit. But when y is 0, r square times 0 will be 0. And 0 cube will still be 0. So actually the lower limit is gone. Okay? So what will come out? 2 pi times r cube minus r cube, this is over 3. You multiply this by 3 over 3. Okay? So you can combine now. 3 minus 1 will be 2 r cube over 3. So volume will be 2 pi 3 cube r cube minus r cube over 3 is actually 2/3 r cube. So 2 times 2 will be 4 over 3 r cube. So this is the formula for taking the volume of a sphere in terms of the radius. Okay, 4/3 pi r cube cubic units. Why cubic? It's volume, guys. Volume. It's 3 dimensions multiplied by 3, that's volume. It's just like, I will give you an example of this. A rectangle, you know the area of this one, length times width, to compute for the volume multiplied by the thickness. So actually volume is 3 units multiplied by itself 3 times. So this is actually cubic units. So I will repeat it for the last time, guys, before we go this afternoon. Volume for a sphere will be 4/3 pi r cube. Okay? That is the general formula for taking the volume of a sphere as a function of the radius. This is cubic units. So if you are designing a water tank in the form of a sphere, if you got a 3-meter diameter, what will be the volume of the water that could be accommodated by that sphere water tank? You could compute for it, guys. And the proper way to solve for that one is volume equal to 4/3 pi r cube cubic units. So if it is in meters, that should be cubic meter. If the radius is in feet, it should be cubic feet. If it is in inches, it should be cubic inches. So volume is actually a measurement multiplied by itself 3 times. That's why it is cubic units. Okay, good afternoon, Los Angeles. That's the formula for taking the volume of a sphere as a function of the radius. That's the derivation. Okay, good afternoon, Los Angeles.